Hello friends, so in this lecture we will understand some laws that are associated with the hydrostatic pressure. So first law, or simply law that we are defining here, the first one is the Pascal's law. So first we are defining Pascal's law. Right, this is okay. Pascal's law. So in Pascal's law, what is the Pascal's law? So we are considering this is the free surface of fluid. So this is the marquee here, and in this free surface that I'm considering a fluid element here. So I'm considering a fluid element here. So let this distance that I'm taking, this is dx, that is along x-axis. This one is dy. This is ds, and let we are saying this angle is theta. Right? This is the fluid element of dimension dx, dy, and ds, and it's an angle theta. Now I'm considering this triangular shape element because I want to analyze the intensity of pressure. The intensity of pressure at particular point is variable or not with respect to direction. Means if the direction is going to change, is the pressure intensity also going to change or not? So what I'm saying, on this element Px is the pressure intensity that is acting on this face that I'm marking. This is A, B, C. This is alright. So Px is the pressure intensity that is acting on this AB face, that is in x direction, and let Py is the pressure intensity that is acting on the face AC in y direction, and let P theta is the pressure intensity that is acting on BC phase. So now, as we know the pressure intensities everywhere on this element, now if I'm saying this element is very much small, so the dimension dx, dy, and ds is also very much small, so we can ignore the weight. So weight of this element is equals to 0. So actually we can consider this is approximately a point. This element is look like a point. Now, so first of all, this is the element, and this element of fluid is lying in a static fluid, means fluid which is at a rest condition. Alright, so now first I will consider the forces that is acting in x direction. So we are considering forces that is acting in this x direction. So that we are talking, that is forces acting in x direction for equilibrium state. Now, so first of all, Px is the force intensity, not the force, and pressure is a scalar quantity, so we can't resolve the pressure also. So force that is acting on this face AB is actually the pressure and the area. So here the area of this face AB is dy into unity because the width of this face is unity. So I think that is this force that is px into dy into 1 is acting in positive x direction. So I can write that is, this is px dy into 1. Just a minute. So this is acting in positive x direction. Now on this face, BC face, so on the BC face the force is p theta into ds. ds into 1 is the area. So p theta, that is pressure, into area is the pressure force. So pressure force on the face BC is p theta into ds into 1. But this is not acting in x direction, so we can take component here. So if I am drawing that a line here and also a line here, so we can say that if this is theta, this angle is theta, this is also theta, right? And this blue line and this p theta are perpendicular to each other, so this angle is 90 minus theta. Now both this line and this line are perpendicular to each other, so at this angle is 90 minus theta, this is theta, right? So the force that is acting along x direction will be, so p theta is not a force, p theta is the pressure intensity, and pressure is scalar quantity, we can't resolve the scalar one. So first the force, so force is p theta into ds, that is multiplying by area. Now this is the force, this force is acting perpendicular to the BC. So the component of this force that is acting along in x direction is, so resolving towards this side, so we can say that this force is equals to what? So if I'm resolving along the theta side, this will be cos theta. If I'm resolving along this side, this will be sin theta. So this is p theta ds sin theta. Alright. So again, the direction of this force, in a negative x direction. So I'm taking minus sign here. I'm writing this is p theta ds into 1, that is the force, and x direction this is sin theta. Alright. Now any other force that is acting in x direction? No, there is no force. Now if this fluid is in motion, then the net force in the x direction will be equal to the inertia force in the x direction. But as the fluid is at rest condition, there is no inertia force. So for the equilibrium state, the net force will be equal to 0 here. So we can write this term, that is px dy minus p theta ds sin theta equals to 0. Now look at this triangle ABC. So that I'm making here the triangle ABC. This is right triangle. So this is A, this is B, this is C, and this angle is theta. This is ds, this is dx, and this is dy. So from this triangle consideration, I can say that is ds sin theta is equals to dy. You can see here ds sin theta is equals to dy. So we can replace this term by dy. So I'm replacing here. So this is px dy minus p theta dy is equals to 0. So from this one dy here, so we can write that is px minus p theta equals to 0. This is out, and we can write now that is px is equals to p theta. So from the consideration of the forces in the equilibrium state in x direction, we can say that that is pressure intensity in the x direction, that is px, is also equal to the pressure intensity on this plane BC, that is p theta. That I'm saying this is our first equation. Right. Similarly, I'm considering the forces in y direction. So that I'm saying that is forces in y direction. Alright. So forces in y direction. So first we are saying this one, that is Py. So Py is the pressure intensity and area of this plane is dx into 1. So simply this is dx. So we can write, and this is acting in positive y direction. So we can write this is Py dx. Now for this one, p theta, that is acting on BC plane. So the component of this force, the force is p theta ds, that is acting in y direction, will be p theta ds cos theta, this one, and this is acting in negative y direction. So I can write that is minus p theta ds cos theta, negative direction. So this is negative. Also the weight of this element can act in y direction, in downward direction, but as we are saying the dimension is very much small and this element is approaching to a point, the weight of the element we are considering approximately 0 here. Now again the fluid is static, there is no movement of fluid, so the net force will be equals to 0. So again considering this triangle ABC, we can also say that that is ds cos theta is equals to dx. I can write ds cos theta is equals to dx. You can see here ds cos theta is the projection, that is equals to dx. So I can replace this term. So I can write py dx minus p theta dx is equals to 0. Again this will out, so we can write that is py minus p theta is equals to 0. So we can write that is py is equals to p theta. So means consider the forces in y direction, our conclusion is that again that is py is equals also equals to p theta. This is our second equation. So from our first and second equation we can conclude that that is px is equals to py equals to p theta. This is the Pascal's law, and the statement of the Pascal's law is that that is the pressure intensity at a point in static fluid remains same in all direction. Right, again that I'm saying the statement is that the pressure intensity in static fluid remains same in all direction. So let, if I am considering a point in the static fluid here, so I don't know what is the magnitude of the pressure intensity here at this point. I don't know what is the magnitude, but whatever is the magnitude, the intensity of pressure will remain same in all direction. This intensity of pressure at this point will remain same in all direction. Means the magnitude is not going to change in static fluid of the pressure intensity. This is the Pascal's law. Alright, so at this point the pressure intensity in this direction, this direction, this direction, this direction, this direction, any direction is remains same. That's our Pascal's law. Alright. This law is very much interesting, and the application of this law are also interesting. So let's see one application here. So I'm considering a tank like that. Like that. Alright, this is a tank here. This is connected with a pipe here. This is another some vessel and something else. So now let in this tank water is here. This is filled with water. As this is connected with this pipe, so is also water, and this vessel is also water. This container also water. And level of the water both sides will be same up to this point. Alright, so both sides the level of the water is same here. So now from the Pascal's law we know that is at the same level the pressure will remain same, like that. That is Px equals to Py equals to Pz. So we can say that there is pressure intensity at this level and pressure intensity at this level is same. So let I'm saying here, let pressure intensity is, that I'm changing the color here, that here the pressure intensity is Pa, and let here the pressure intensity is Pb. Alright, and we know that is Pa is equals to Pb. Alright, now let I'm saying the area of this container, cross section area of this container is that small a, and area of this container is that capital A, and let I'm assuming that is capital A is 100 times of small a. That if I'm saying this thing. Alright, so in this case the pressure force over this layer, so if I want to calculate the pressure force, this is the pressure intensity, A is the area, so the pressure force that I'm saying over here, that I'm saying this is Fa. So Fa here will be pressure intensity into area, and pressure force over here, so this is B here actually, over here, that I'm saying this is F, this is also B here. Fa is Pa into A here. Alright, so we can write Pa. So Pa we can write that is Fa divided by area. So I can write this is Fa divided by area, small a. Similarly Pb I can write that is Fb divided by this capital area A. So this is Fb divided by A. Alright, so as we are saying that is capital A is 100 times of small a, so I can also write that is this is also equals to Fb divided by 100 times of small a. Alright, so means we cancel out these terms, so we can write by this equation that is Fb is 100 times of Fa. Alright, Fb is 100 times of Fa. So as the pressure intensity is same, but the force is different. So let if I'm saying I'm using a 100 Newton weight here. Here the weight is 100 Newton. This is 100 Newton. There is a weight, and let here the weight is 1 Newton. So here the weight is 1 Newton, and here the weight is 100 Newton. So this is the force. So the force is 1 Newton here, force is 100 Newton here. So you can say this one, that is this 1 Newton. This 1 Newton is what? This 1 Newton is Fa. This 1 Newton is Fa. So Fa is 1 Newton and Fb is 100 Newton. Alright, so you can see this equation. That is Fb is 100 times of Fa. So means I can balance this 100 Newton force by 1 Newton force here. I can balance this 100 Newton force by 1 Newton force here, because as the pressure intensity is same here, so as the force is 100 Newton, the area is 100, so in that case the pressure intensity is 1, and here the force is 1 Newton, area is small a, that is 1, so the pressure intensity is again 1. So again the pressure intensity remains same. This concept is used in hydraulic machines. So if in hydraulic machines I want to lift 100 Newton of weight, in that case, so here the area will be 100 in this case, so I will use only 1 Newton of force here over this 1 meter square area, and I can easily lift this weight here, or I can easily balance this weight here by the use of 1 Newton only. Alright, so this is, you can see here, this law is very much interesting law, that is termed as Pascal's law. And Pascal's law is what? Pascal's law states that in a static fluid at a particular point the pressure intensity remains same in all directions.